So we're talking about resistors in parallel today. Yesterday we talked about resistors in series. Now, first off, how do you recognize resistors in parallel? These two resistors are in parallel. Yes, they're geometrically parallel. See this? They're geometrically parallel, but is that why we call them parallel? No. What's the defining characteristic for resistors being in parallel is that the circuit branched. So let's start at the battery and look at the current. So the current comes out of the battery. Current is always positive charge motion. If you had a positive guy right there, he's going to go away from the positive terminal. So we're going to call this current I. Now current I comes up like this. Now what happens here at point A? At point A, the current that was labeled I splits. It splits into I1 and I2. So notice that these two resistors here are on different branches of the circuit. That is the characteristic of parallel. Whenever a circuit splits, you have a situation where it's parallel. Now real quickly, I want to show you guys something. There's two ways to diagram circuits. There's this super boxy way. Let's call this approach the super boxy way. Now watch this. This circuit that I'm drawing is the exact same thing. Exactly the same. This is another way you'll see circuits drawn. There's two different styles. That's a 12-volt battery. Here's the 6 ohm. Here's the 3 ohm. So look, all that's happening, see this point right here? This point is where the circuit splits. That's this point, right? These 2 points are identical right there. Okay, and then this point is where the currents come back together again. Boom, that's this point. So let's label the currents up. The current coming out of the battery, I, like this. I comes in like this. Now what happens to current I right here? Well, this current going up through here is called I1. This current here is I2. I1 comes down like this. I2 like this. So what current do we have here? We're back to I. Bam. Like that. So there's 3 currents in this circuit. Okay? Now, let's talk about something here. Things to know. Number 1, when you have resistors in parallel, current is not the same. I want you to remember this phrase. My mom always said it when I was growing up. She'd be like, Michael, don't follow the path of least resistance. Did I mention this yesterday? Any of your parents ever say that to you? Don't follow the path of least resistance. Did your parents really?
Said in Chinese.
Right. Because like, you guys know the path of least resistance in life, it's like, you know, you got the hard choice and you got the easy choice. If you always make the easy choice, you know, things don't really work out very well. So my mom would always say, Michael, don't follow the path of least resistance. It's a physics phrase. So what do we mean by the path of least resistance? Well, look. So look at current I right here. So current I hits this junction right here. In fact, let me clean this up. Let's revert this back. Okay, so current I hits this junction that's labeled point A. Which path has higher resistance? We'll call the top path, we'll call this path 1. We'll call the bottom path path 2. Which path has more resistance? Path 1. So which path is going to get more current? Path 2. The path of smaller resistance gets more current. Am I saying that the path of high resistance gets 0 current? No. It's just it gets less. Now, 6 and 3 are mighty fine numbers. They're kind of nice. What do you notice about 6 and 3? Well, 6 is double 3, so let me ask you a question. Let's look at I2 here. How much bigger, so this is going to be the bigger current, right? I2 is larger, I1 is going to be smaller. How much larger will I2 be compared to I1? It's going to be twice. Do you want to know how I know that? Because path number 2 has half the resistance, right? So the phrase to remember, current follows the path of least resistance. Now, dudes, flashback to yesterday. Resistors in series. What was true for resistors in series? The current is what? The same. Even if they're different resistors, 6 and 3, you're still going to have the same current, right? Current in series is the same. The thing I'm pointing out here, the two things that are true for series, you guys know what I'm talking about, the two things right here? These two things right here. The two things that are true for series are oppositely true for parallel. In series, current is the same. In parallel, current is not the same. All right, let's look at voltage now. Actually, scratch that. Let's talk about how you simplify resistors in parallel. Okay? Resistors in parallel. We got a 6 and a 3. Here's the thing that's always going to be true. When you simplify resistors in parallel, the equivalent resistance will be smaller than the smallest. Okay? So for example, 6 and 3. Which one's smaller? 3. This equivalent resistance will be smaller than 3. And if you don't get that, you made a mistake. Now, here's how you calculate it. So I call it the 1 over equation. Let's do this calculation. So we're going to go, what is this equivalent resistance? We're going to go 1 over the equivalent is going to be 1 over 6 plus 1 over 3. But 1 over 3 is 2 over 6, right? Just to make the denominators the same. So now we have this. We have 1 over the equivalent is 3 over 6. But 3 over 6 is just 1/2. I've seen the following mistake a lot of times. Kids go like this. They're like, oh, okay, so the equivalent is 1/2. True or false?
False.
False, because you got to flip it now. You got to go, okay, flip that. So the equivalent is going to be 2. Now notice, like I said, the equivalent resistance is smaller than the smallest, right? Now, dude, just real quick, go back to series. Here's resistors in series. What happens if you have resistors in series? 6 and 3, what are you going to get? 9. So, dude, resistors in series increase the resistance. Resistors in parallel decrease the resistance. And there's lots of cool examples. I think tomorrow I'll bring in, you can do this with straws. It's not just, what I'm telling you here, it's not just true for electrical circuits. It's true for like water through a pipe, you know. Let's say you're setting up a sprinkler system, if you branch off the sprinkler system, you're dropping the resistance for that water flow. You know what I'm saying? Like if you have a water pipe like this, and it branches off like this, you know, into 2, what's going to happen to the resistance when you branch it? It's going to drop. Okay, what else do you have to know here? Move it on. Okay, second idea. Voltage is the same. Okay, let's look at this. When you're doing voltage, here we have a 12-volt battery. So it goes 0 volts, 12 volts. Did I have to go 0 and 12? No. I could have done like 10 and 22. I could have done like 30 and 42. As long as the difference is 12, that's fine. Okay, so how many volts do we have right here? 12. How many volts do we have right here? 12. How many volts up here? 12. The only time you're going to change your volts is when you cross a battery or a resistor. When you cross a battery, that's a voltage gain. See right here? As the current comes through, the current comes in like this. As you cross the battery, you're going from 0 to 12. And that makes sense, because what's a volt? A volt is simply what? Energy per coulomb. It's joule per coulomb. So in the battery, there's an energy gain, or what we call a voltage gain. And in the resistors, it's a voltage loss. Now, how many volts do we have right here? 0. How many volts right here? 0. How many volts right here? 0, right? Because we didn't cross a battery and we didn't cross a resistor. Now, check it out, guys. For the charges that go across this path, right? Because some of the charges are going to go through here, like this. What's the delta V across this resistor? 12 on this side, 0 on that. 12 over to 0. What's the delta V? 12. Okay, now look at this guy. For the charges that go across this guy, like this, 12 on this side, that's the same thing. What's the delta V across this guy? 12. Voltage for resistors in parallel. I don't care if you have 2 resistors in parallel, or there even could have been a third resistor. We could have put a third resistor on here. And then this would have been 12 right here and 0 right there, right? The delta V across that guy would have been 12. Resistors in parallel have the same voltage. Okay, now I think I've covered everything. And by the way, what was true for resistors in series for voltage? If you have resistors in series like this, like 3 ohm, are these guys going to have the same delta V across them, or different? Different. The two things that are true for series are oppositely true for parallel. Okay? Should you memorize these two things, or should you understand it? Understand. If you understand it, it's way better. Like light years better. Now, we're not done. Don't pack up, dude. We got 2 more screens. Now, power. You're going to like this page, dude. You're going to like this. Basic definition for power. And you learned this first semester. Power is energy per time. What's energy? Joule. What's time? Second. What do we call a joule per second? A watt. Now, another way to look at power, work. Joule, time, second. What's a joule per second? Still a watt, right? So sometimes you're going to look at power this way. Other times you're going to look at it that way. It's the same thing, joules per second. Now, you ready for this? This is going to break your brain. You're going to be like, whoa, watch this. It's pretty bomb. There are 3 equations for circuit. I call them the circuitry power equations. The first one is P equals current times voltage. What? Watch. P equals I, which is current, times voltage. What do we measure current in? Somebody knows. Don't be shy. Coulombs per second. And what do we call a coulomb per second? That's called a what? That's an amp. A coulomb per second is current. What do we measure voltage in? Joules per coulomb. Joules per second is watt. Now look what happens here. What happens to the coulombs? Bam! What do we get? Power, baby. If you multiply the current times the voltage, it comes out as power. Ba-bam. Now, how do you get these other 2 power equations? What you do is you take Ohm's law, because here's the deal. For the multiple choice part of the AP exam, no equations. So here's what you do. Memorize this one. It's like the master power equation. Memorize this one, and then how do you get the other ones? Take Ohm's law, plug it in. So if you plug Ohm's law in down here, what do you get? P equals I squared R. And then to get the third one, just rearrange Ohm's law. If you rearrange Ohm's law, you get I equals delta V over R. Bam! Plug that in. You like this, don't you? Okay, those are the 3 power equations. Now, we're not done. One more screen. I'm going to get you started on worksheet number 1. This is where it all comes together. This is where the rubber hits the road. Everybody got this copy? Okay, so now you know how to do power. Okay. Now, this is worksheet number 1. I'm going to erase this text. Now, real quick, look, see this picture right here? I'm going to draw it up for you the other way. The other way you're going to see this drawn is like this. Just make note of this. Copy this somewhere, because you're going to see these circuit problems both ways. Sometimes you're going to see the circuit drawn like this. So these 2 pictures are identical. So 2 ohm, here we have 3 ohm, 1 ohm, 4 ohm. All right, let's label up the currents. The worksheet says to use I1, I2, I3. So whenever you do currents, start at the battery. So this current coming out here, let's call this one what? I1. Okay, so I1 comes like this, bam, right to there. Now what happens right here? I1 what? Bifurcates. Splits. If you want to sound cool, bifurcates. Bam! What should we call this current? I2. I3. So I3 goes around like this. What current are we back to right here? I1. Now, so we've labeled all the currents. Notice this diagram on the right, same thing, dude. It's the exact same thing. I1 comes like this. There's I1. This current here we labeled I2. This current here is I3. They come back together again. You're back to I1. It's the same thing. All right, now look. The key, and I'm 60 seconds away from done. Ready? Maybe 90. Not more than 240. Okay. The key to doing circuits is simplified pictures. What's the first thing you want to simplify in this given picture? The 3 and the 1 are in what? Parallel. Because what happens right here? What happens right there? It branches. So the first thing you want to do, simplify the 3 and the 1. So you go like this. Go bam. We're going to just redraw this picture simplified. It's the key to doing circuits. The key to a circuit problem is simplifying the circuit. So all I did here, is I simplified the 3 and the 1 into 0.75. Real quick, I know some of you are like, Spaldo, where did you get the 0.75? Here's what I did. For these two right here, 1 over the equivalent is 1 over 3 plus 1 over 1. When you do the math, the equivalent comes out as 3/4, 0.75. Okay? Smaller than the smallest. All right, now, what current is in this circuit? What current flows around this? There's a current here. What current is it? Is it I1 from this diagram? Is it I2? Or is it I3? It's I1. So label it I1. Bam. This is I1. All of them, because current in series is the same. Okay, now, these 3 resistors, these guys here, 1, 2, 3, those guys are in what? Series. So how do you simplify resistors in series? You add them up. So it's going to be 6.75. This is 18-volt battery. Now, what current is in this guy? I1, right? It's the current up here. So look, this current here is the same as this, right? Those currents are all the same. So in general, the way you do a circuit problem, here's how you do it. Ready? It's the biggest thing I can show you. You take the circuit, you break it down to one resistor. Simplify, 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 and then show all the pictures along the way. Once you've simplified it, then you work your way back up. Then you break it down, and then you go like this. Like what I would do here, first find what I1 is. What's I1 going to be? I1, using Ohm's law, delta V equals IR. So what's I1 going to be? It's going to be delta V over R. Do we have the delta V across this guy? Well, let's see. 18-volt battery, that means 18 and 0. So here we have 0. Here we have 18. Ah, that's easy. What's the delta V across that dude? It's 18 volts. Hey, man, is the delta V across this 18? This is a, dude, do you want to know how to tell the AP grader or me that you have no idea what you're doing? This is the number one thing. Ready? The number one thing that kids do to reveal that they have no idea what's happening is they go like this. They're using Ohm's law, and they go, ooh, there's a V, and they always plug in that. Like, ooh, boom, plug it in. Is the delta V, is this guy 18 volts? No, 18 volts is from there to there. But what happens is, you go, there's 18 volts, there's 0 volts. As you go around the circuit, your voltage comes back to 0. Your volts come back to 0, right? So anyway, find I1. So this is 6.75. This comes out, I think it's 2.67 amps. So okay, so this current here is 2.67 amps. So what's the current here? 2.67 amps. I hope it's 2.67. I'm doing that off memory, which ain't so good. Bam, like that. What's the current right here? 2.67 amps. You start filling it in. Circuitry is like a puzzle. You start to fill it all in. You're like, okay, so I found that. All right. Good job. We're done.